Hi everyone, this video is one about the long-run behavior of a few different types of functions. Now, long-run behavior means the limits as x goes to plus and minus infinity. In the long run, what is happening? You're going to see in this video that functions in the long run can do a number of things. In the long run, the limits as x goes to plus or minus infinity, a function might do this. In that case, both long run limits would be positive infinity. A function might do this. In that case, the limit as x goes to positive infinity of the function is infinity, and the limit as x goes to negative infinity of a function is negative infinity. A function could also potentially do this or this, this and this, I should say. Both limits in the long run are negative infinity. A function could do this. And a function could also have, in the long run, could have a horizontal asymptote. So, for example, maybe a function does this in the long run, has a horizontal asymptote of 0. Or maybe a function does this in the long run, has a some other horizontal asymptote of, let's call this, just for kicks, we'll call it 3 in this case. The limit as x goes to infinity is 3. The limit as x goes to negative infinity is also 3. So that's what we're talking about here. Long-run behavior, limits as x go to plus or minus infinity. And remember, the answer to a limit question is an output. It's what the function, what f of x approaches. So let's start with a of x is equal to 5x squared minus 3x plus 1. Now this is a polynomial, and polynomials, we can, if we want to answer long-run behavior, all that we have to do is focus on the lead term of the polynomial. Keep in mind, the lead term might not always come first. Like in b of x, the lead term is negative 3x cubed. In a of x, it's 5x squared. The lead term is the term with the largest exponent that you see. If you focus on the lead term, whatever this lead term does is what the polynomial, the entire thing, will do in the long run. But we don't need to worry about negative 3x plus 1. We focus on 5x squared. So in the long run, what does 5x squared do? Well, you should know what 5x squared looks like at this point. And 5x squared is a upward-facing quadratic, which in the long run is going to do this. Again, in the short run, we don't necessarily know what this function does. Maybe it dips way down here. Okay, maybe it never crosses the x-axis. We don't necessarily know. If we took some time and thought about it, we could figure it out. We could plot it on our calculator. But big picture, in the long run, we know that 5x squared is going to do this. And so we say that our long-run behavior is the limit as x goes to infinity of a of x. The answer to this limit question is infinity. And in our second piece, the limit as x goes to negative infinity of a of x is also positive infinity. Both long-run behavior, in this case, both go to positive infinity. Let's move on to b of x. So b of x, also a polynomial, has a lead term of negative 3x cubed. So what does negative 3x cubed look like? Well, again, it's your job to know these basic, positive 5x squared, negative 3x cubed. You should know what those look like after a pre-calculus course, or throughout a pre-calculus course. You should be learning that. Negative 3x cubed looks like this. In the short run, again, we've got these other terms here, and so that's going to cause some potential change, maybe as much as 2 changes in direction in this case. Okay, we don't necessarily know exactly what that looks like. We don't care. This is about the long-run behavior. And negative 3x cubed in the long run has a limit as x goes to infinity. We would say of b of x is negative infinity. That's this. And the limit as x goes to negative infinity of b of x is positive infinity. That's this. So again, if it's a polynomial, you focus on the lead term only. Whatever that lead term does is what your polynomial will do. Now, c of x is not a polynomial. C of x is a rational function. And a rational function is a polynomial divided by a polynomial. For rational functions, you need to focus on the lead term of the numerator, in this case 11x to the 5th, the lead term of the denominator, in this case negative 2x cubed. Clean that up. So I'm going to rewrite this as 11x to the 5th over negative 2x cubed. And when we clean that up, we get negative 11 halves x squared. Whatever the cleaned up version does, is what this whole function will do in the long run. So what does an even powered power function with a negative lead term do, or lead coefficient is what I meant to say do? Well, negative 11 halves x squared is going to be a downward facing quadratic, like that. And so hopefully you can see that the limit as x goes to infinity is negative infinity, and the limit as x goes to negative infinity is also negative infinity. We would write it like this: the limit as x goes to infinity of c of x is equal to negative infinity, and the limit as x goes to negative infinity of c of x is also equal to negative infinity. Now's a good time to say that you can see, I hope, from these first three examples, we do not need to graph the function. We don't need to spend our time graphing the function and trying to find a window that fits and all that. If you know what these positive ax squared, negative ax cubed, negative ax squared, if you know what those look like in the long run, you can answer your long run behavior without graphing, without using the table. Now you can, if there's time, if this is a homework assignment, let's say, I would encourage you to go ahead and jump. The fastest way to do this is go ahead and go to your table. Of course, you'd want to, in this case, wrap this in a pair of parentheses and wrap this in a pair of parentheses, and then go to your table and put in increasingly large values of x and see what the y values the outputs approach. You're going to see that they head to negative infinity, and put in increasingly negative values of x, and you'll see that those values head toward negative infinity as well. All right, let's take a look at d of x. So for d of x, we have 4x plus 1 over 5 plus x plus 2x squared. Again, we have a rational function. We focus on the lead term over the lead term, and we clean that up. Now 4x over 2x squared cleans up to 2 over x, also known as 2x to the negative first. But I'm going to focus on 2 over x. 2 over x, okay, 2 over x looks very similar to 1 over x, and 1 over x looks like this. And so what I hope you'll see is that in the previous three examples we had some combination of infinities for our long run behavior. Now we actually have a horizontal asymptote, and that horizontal asymptote is 0. And I know it's 0 because as x gets bigger and bigger and bigger, okay, so trace the function out this way, as x gets larger, the denominator blows up, and as the denominator blows up, if we have a constant divided by that denominator, it's going to go to 0. Same thing as we go this way. As this value becomes more and more negative, our outputs will go to 0. You can determine that from the table, but even faster if you know what the basic function 2 over x, which is very similar to 1 over x, looks like. It's going to save you some time. So we'd say in this case the limit as x goes to positive infinity of d of x is 0. Remember, a limit, the answer to a limit question is an output, it's a y value. And the limit as x goes to negative infinity of d of x is also 0. Check it out. Graph this function or go to your table and you'll see that those are 0. Okay, the second half of this video, I want to look at two more, I should say, rational functions. Remember, a rational function, again, is a polynomial divided by a polynomial. So we've got a polynomial over a polynomial here. And we're going to start with p of x. Now I want to know the zeros. So remember, a 0 by definition is where a function intersects the x-axis. It doesn't have to necessarily cross. It could bounce. So for example, if I drew this function, okay, it has a 0 here, it has a 0 here. It's got two zeros. So the question is, what are the zeros of this function? And the rule is, if I want to determine the zeros, then I find the zeros of the numerator. Find the zeros of the numerator. Well, in this case, we need to factor the numerator to find those zeros. Again, you could graph that, but you're going to be a lot more efficient if you factor it. So 5x squared minus 4x minus 1 factors into the quantity 5x times something times the quantity x times something. In this case, you can play around with it to double check me, but you're going to get an x minus 1 and a 5x plus 1. That will give you your 5x squared minus 4x minus 1. Now, if I want to know where that's equal to 0, I set this factor to 0 and solve, and I set this factor to 0 and solve. If you set 5x plus 1 equal to 0, subtract 1, divide by 5, you're going to get a 0 of x equals negative 1/5. There's one of your zeros. And if you set this factor equal to 0, you'll get x equals 1. And so if we were to graph this function here, the whole function, you would find that it intersects the x-axis at x equals negative 1/5 and 1. Do it. Check it out. Double check me. Parts B and C are very similar to what we just covered on the previous slide. If I want to know the limit as x goes to infinity of p of x, then in this case, I am going to focus solely on the lead term of the numerator over the lead term of the denominator. Okay, 5x squared over 7x squared reduces to 5 over 7. Now, just like in the previous slide, I'm sorry you did not see an example like this now that I think of it, we get a constant, 5 over 7. Anytime you get a constant, okay, with your rational function like this, your long-run behavior, that means that this is going to be a horizontal asymptote. So if we plotted this function, we would find that at x equals 5 over 7, this function is going to have a horizontal asymptote. Now, if you graph it, you'll find that it approaches, the function in the long run is going to approach that line. So we would say that the limit as x goes to infinity of p of x is actually 5 over 7. And the limit as x goes to negative infinity of p of x is also 5 over 7. So one more time, in the previous slide, we had limits of infinity, combinations of infinities. We ended up with a limit of 0, and that's going to occur, the more you do these, you'll see a pattern. That will occur anytime we end up with, after cleaning this up, anytime we end up with some x to a power in our denominator, our limits will be 0. But if we're left just with a constant, notice there's no independent variable, there's not an independent variable in the numerator or the denominator, we just end up with a constant, then in that case, we know that our limit is going to be whatever that constant is. It's a horizontal asymptote. Part D, the y-intercept. If I want to solve for y-intercept, universally I'll put 0 in for x. So if I put 0 in for x into my original function, okay, think about it, you'll get a negative 1 in your numerator, you'll get a 13 in your denominator, and so the y-intercept is negative 1 over 13. That means that our graph will have a y-intercept at negative 1 over 13. Vertical asymptotes. In order to determine a vertical asymptote, we set the denominator equal to 0 and solve. So we're trying to determine now if there's ever a time that 13 plus 7x squared would be equal to 0. Again, this is when working with rational functions. Now, if you think, let's think through this critically for a moment. Any value squared, so take anything and square it, you're going to get a number greater than or equal to 0, which means that this piece in itself will always be greater than or equal to 0, which means that this as a whole will always be greater than or equal to 13. And so it's not possible for this to equal 0, therefore there are no vertical asymptotes in this function. To close, let's look at q of x. So q of x is also a rational function. In this case, 3x squared plus 2x minus 1 over 11 plus 7x. I want to find the zeros. Again, I'll set the numerator equal to 0 if I'm trying to find the zeros of a rational function. So I'm going to factor 3x squared plus 2x minus 1. 3x and x. You can see that you do have to have some factoring skills, some background in factoring if you're going to be able to do a lot of these problems. And we're going to say, after thinking about it for a moment, I'm going to make that a plus 1 and a minus 1. I can always double check. There's my positive 3x. There's my minus 1x. That gives me my positive 2x I'm looking for. And then we know we have 3x squared because we got 3x times x, and we know we have minus 1 because I got negative 1 plus 1. So that works. Now this factor, what's going to make 3x minus 1 equal to 0? Well, if we add 1 and divide by 3, we'll get x is a third. So there's one of our solutions. There's one of our zeros. That's an input or an x value where our function will intersect the x-axis. And if I said this factor, x plus 1 equals 0, we're going to get x is equal to negative 1. And so our second 0 is x equals negative 1. If I want to determine the long-run behavior, again, so you're seeing this for the 5th or 6th time now. So if I want to determine the long-run behavior, what's the limit as x goes to plus and minus infinity? Again, you focus on your lead term over the lead term. So I'm going to say 3x squared over 7x. And when I clean that up, I get 3x over 7. So now we need to think about, well, what does 3x over 7 do in the long run? Well, 3 over 7x is a linear function that's increasing because the slope's positive, so it's going to do that, which tells us that the answer to these two prompts, the answers to these prompts, the limit is of q of x as x goes to infinity is infinity. And we can see that right here. And the limit as x goes to negative infinity of q of x is negative infinity. And we can see that right here. Again, if you want, plug this in. Use your table. Put increasingly large, again, you'll wrap the numerator and wrap the denominator, but put in increasingly large values of x, and you'll see that takes off without bound toward infinity, and that takes off without bound toward negative infinity. For the y-intercept, universally, we'll put 0 in for x. Go back to your original function here. That's going to become 0. That's going to become 0. We're left with a negative 1 in our numerator. Okay, that will become 0. We're left with an 11 in our denominator, and so our y-intercept for this function is going to be negative 1 over 11. It's going to have a y-intercept down here again below the x-axis. Last but not least, vertical asymptotes. If you have a rational function, which is a polynomial divided by a polynomial, you set your denominator to 0. So 11 plus 7x is equal to 0. I'll subtract 11. I'll divide by 7. And I have a vertical asymptote in this case of negative 11 over 7. Double check, graph the function, you will find that at negative 11 over 7, this thing is going to have a vertical asymptote. All right, that's all I've got.